be also considered the same vector, yes or no? But your program will scale the first, if you say my vector A equals AB. But if you do it that way, then as I said, your program will scan first coordinate here and say you are not 2, 1, you are not my vector, and it will discard it. Don't you agree? So what do we say? Are they all kind of instances of our vector? So generally what we are saying is the following. That equality among the vectors is relaxed. We are disregarding their starting point. Agree? We are saying basically, well, what's vector? Start wherever you want and then go one step right to up, that you will catch what we need from vector. Agree? So how can you do that? You are actually relaxing equality. And that's what equivalence relations are. Really, this free language, don't use this except in private. Setting a relaxed equality. Something similar. Look at these two charts. Are they the same or not the same?
So do you use I and J instead of...
Let's say?
You use like I and J?
We can talk about, I'll go back to this more complicated example, but the main idea about that relaxed equality, if I look at these two charts, these are definitely not the same charts. Why? Because you immediately notice that they are not on the same spot. So one is right from this line, one is left from this line, they are not the same object. Okay? But I say the following, I don't care which chalk I hold, as long as it gives me the same service. That means if I can write equally well, if one is long, one is short, I cannot say they're the same chalk. Okay? They are more or less the same length. Are they for my writing purposes the same, yes or no? So I treat them the same chalk, even if they are not the same object. That's why I say a relaxed equality. So from full equality, that in mathematics and everywhere means absolutely the same object. Nobody is equal to nobody else except itself. Here you allow to relax some property and say, if they differ just in that property, it doesn't matter. I'll treat them as being the same. Agree? And then we have these objects have the same magnitude and direction, so I will consider them as the same object. But equality is very strict, so that's why I'll say the following. Instead of saying AB equals CD as segments, so we call oriented segments, AB, and then I look at the segment CD, I'm not going to say that they are equal, I will say that they are equivalent, or I'll use tilde. So AB is equivalent. Didn't you use the same thing? Are these two triangles the same? No, but they are in a way equivalent in shape. If I only care about shape, they have the same shape. If I make equivalence relation, if three triangles have the same angles, I'll consider them the same shape. Then these two are equivalent. Is that okay? So that's the idea of equivalence relation, and we use that very often. So how would you define a vector? And if you open the calculus book, you will see. I always have problems when I teach this in Calc 3 to people that never took discrete. How do I say this if they don't know the language? And the language says, what is a vector? Vector is an equivalence class. That's what we call it. Equivalence class of a parallel oriented segment of the same length and orientation. So, if I look at all these segments, as segments they are not equal, do you agree? But all together they kind of give me the idea of vector. So who of them is a vector? All of them. Each of them has equal right to be representative of that class. So whole that group is called a vector, and it's called equivalence class. I'll explain that more precisely in a second. But equivalence class means all together. If you want to pick up one, pick whichever one you like. They are all considered to be the same as vectors. As oriented segments, they are not the same because I see different starting point. But as vectors, I will treat them. So let me give you another example before I go to the main theorem of the day, actually, that actually talks about equivalence relations. And that would be problem similar to yours. And that problem is, how would you define rational numbers or fractions? Quotient of two integers, like this. 3/5. Is that clear? What if someone writes 6/10? So how would you instruct your machine how to recognize if two of them are the same? Because, if it scans only 3 and scans 6 here, it will say, well, these are two different objects. So what do you do actually? 3/5 is the same thing as 6/10, which is the same as what? -3/5. Right? So I can make this pair of numbers in a many different ways. You agree? So we suggest.
Well, can you just do what you were talking about with the angle? They look at the same angle and connect these into triangles.
For those rational numbers?
Yeah.
But I don't need to add a geometry. Here's an easy test. If you cross multiply, how much do I get here? What do I get here? And then what do I get here? Because what? When is AB equals to C/D multiplied by VB, you get what? A/dVB equals C/dVB, which is what? AD equals BC. You agree? So then, what am I doing? Among all the pairs, numerator, denominator, I establish equivalence relation. I don't care who you are. What I care is, are you giving me the same ratio? Do you agree? And here's the equivalent example. We'll say, and that's the same thing that you did on the quiz, but just this is for quotient. I gave you the difference of that quiz. So here it is. I'll say the following. Pair AB is equivalent to pair CD if and only if AD equals BC. It's actually here. AD this looks very dry and abstract the way I wrote it. Because here it is. Here's a couple. So someone sees my fraction, scans numerator, scans denominator for the other one, and it checks if that's the same object for my purposes. And I give them instruction how to check it. If AD equals BC, treat them as basically the same. And relation equivalence is exactly that. Maybe not same, but basically the same, or same for my purposes, like these two chalks. Okay? So, let me see, is this equivalence relation? I'll practice what I ask you to do in the quiz. So, is this equivalence relation reflexive? So, what am I asking? Is AB equivalent to itself? You understand that this A comma B is actually A fraction B, but I don't want to impose that notation. This is just a couple of numbers that I scan. So what is the definition? So I don't know if this is true, but I know that this is equivalent to what? Multiply outside ones, multiply inner ones. That's what the rule says. So what do I get? AB equals BA. Is this true? So is this true then? So it is reflexive. The same thing is for symmetric. What? Assume that what? AB is related or tilde CD. What do I want to accomplish? That CD is related to AB. So what do I do? First, you always transfer to equations. All the proofs go, easy proofs go that way. By definition, what does it mean? That AB equals what? But that also implies that CD is equivalent to AB. Why? Because just check it. What does he say? Well, I can maybe write in one more line. That BC equals AD, and then now here it is outside one is BC, inside one is AD. So it is symmetric. What about transitive? Transitive, what do? I assume A, B, tilde CD, and also I assume that CD tilde positive? Yes. So then I know that this is in a way some relaxed quantity. And then one more example. Although I'm not going to do it in such a formal way as in this example. I'll just call this example from the notes, but I'll make it in a more specific way. And we'll follow. I told you many times, example is never a proof, real proof is in the notes, but once you understand privately in a way the example, then very often it's easy to assemble the proof and understand the abstraction. Here it is. Suppose that I have a set of 6 elements. 1, 2, 3, 4, 5, 6. Okay? And I divide this like a country into states. However I want, but as long as they are non-empty. Okay? So for example, who do you want to have in the first state? Let's say 1 and 2 are first state. Second state, let it be 3, 4, and 5. And third state is 6. Is that okay? Like number of partitions, like what I asked you in S8-3. So I divided my country into 3 states. How do we call that officially? Partition. So I have partition into non-empty subsets. So this is partition. Who is in that partition? First set is 1, 2. Second one is what? And last one is what? 6 alone. Now using this partition, I will define an equivalence relation, which is what, like country mate or expression statement. No. So what? I will divine equivalence relation tilde P the following way. If you live in the same state, you are kind of related. So who's related then? 1 and 2 are related. What? 1 is related to 2. Is 2 related to 1?
Yeah.
It's relation. What about here? Is 3 related to 4? 4 to 5? 5 to 3? Backwards? What about balloons? I'm not going to put balloons. Does everyone live in the same state as itself?
Starting strange and reflexive.
And symmetric. And what about 6? Which is alone, just balloon. I said no balloon, but 6 needs. Alright. What happened? I got a relation. What did he tell me about that relation? Exactly as Brandon commented. Is it reflexive?
Yep.
Is it symmetric? Is it transitive? So we take it. Equivalence relation. That equivalence relation, I call it delta P, is an equivalence relation. So after that, yes.
What did you call this equivalence?
Is it tilde or delta?
Oh, tilde.
Okay.
Tilde. This symbol is tilde.
Like TILDA?
Tilde.
Okay.
That's a Greek letter. Tilde. It's similarity. Usually, if you study similar triangles, you have to use that. Everybody uses tilde. But tilde P, because it originated with that partition P. Alright. And let me check that that example on the screen. So what did I do here? I did exactly the same thing, but just it looks more formal, like a real full-size proof. We just which is more abstract and a little cleaner, but basically there's nothing more than on this picture. So let's follow. What did I say here? This relation is an equivalence relation. Why? Here it is. I picked any element X from A. See, this is partition. Does everybody live in one state? Is anyone left alone? No. So everybody's in the state. As single state or anyhow, but any X is in one of the states. Do you agree? Could someone be in 2 states? No, because they are partitioned. They are disjoint. So what? It is in the state. So that guy is related to what? Is it related to itself? Does it live in the same state? And that's what I said here. There exists I such that X belongs to AI. Henceforth, delta P is reflexive because X lives in the same state as itself. then what? Let x and y belong to A and assume that x tilde y. Now what do they belong to? X and y belong to the same state? So can I say that y and x belong to the same state? They are same x and y, so it's common sense. And then again, if x and y are related, and y and z are related, what? X and y live in the same state. This might be worth discussing in general sense. So here are the states. So it says x lives in the same state as y. So x is related to y. And y is related to z. Why is x related to z? What's it? Because x and y have a witness state, and y and z have a witness state. Why does it have to be the same state?
Because for the relationship they need to be living in the same state.
Because y cannot live in two different states. Because it might be in some relation that x lives with y in a state like Kansas, and y and z live in Nebraska. But what happens? Then y lives in how many states? And that's what, because if it's partition, it cannot happen. Exactly, partition guarantees transitivity. So if you are building your relation with x through a state, and you are building a relation with z, it must be the same state because you cannot belong to those states. So partition part, exactly built on this. And that's what I wrote there in the notes. So if it looks too abstract, then basically that's what it means, more precise, right? So what did we conclude here from this example? This is very important. An example, we did the following in this first story. The story says, if I have partition, then I can use it to build equivalence relation. Agree? But what we do even more often is the following. And you already saw that last time, I'll just repeat the story. Instead of doing this, I will recall the story that we did last time, which is congruence modulo 6. Do we remember that? How was that relation? A is congruent B modulo 6 if and only if 6 divides B minus A or A minus B, which is the same. My question is this relation reflexive? Yes or no?
We went over that one.
Yes. So it is reflexive. Is it symmetric? Is it transitive? So this relation is what? Equivalence relation. So congruence modulo 6 is an equivalence relation. And actually, for our course, this is probably the main reason why we study equivalence relation, because we want to study more and understand better this relation. So what happened here? If you remember the story last time, there was a groove here around 0. 0 was related to what? Which number?
6.
Who else?
12.
Because they differ by multiple of 6. Who else? 18. So who's here? All the numbers whose remainder is what? Is there someone who's not there?
Yes.
So who's there?
Almost the remainder one.
1, 7, 13, 19, and so on. So there is what? Then there minus 5 is here as well.
2, 8, 14, 20.
Very good. Negative 4 is here.
Is there more negatives as well?
Yes, of course.
Okay, just making sure.
Million. Who's here?
3. No.
generally what happens. It's not like a minute ago, I had a partition and I build the equivalence relation. Here what happens? Equivalence relation made a partition. So you start from tilde and then you get P tilde out of the equivalence relation. And then, so those states have official name and they are called equivalence classes. So who is this? So this is the state. So here is that theorem. So here is the theorem. It says if A is a set and tilde is an equivalence relation, then the equivalence classes of tilde form a partition. So if you call that partition P, then that partition also, if you use that to build a equivalence relation. So let's fix the language. So what are the equivalence classes? So here it is. Who's equivalence class of 0? Equivalence class of an element, we just put in brackets. If it's clear from the context which equivalence class you are using, you don't have to write it. If it's not, make that like marginal 6 or something like that to remind you which equivalence class are we talking about. Is that clear? If it's clear from if there's only one, then you don't have to write it. So whose class of 0?
Set of 6.
All these. So let me write them now as a set. It is set 0, negative 6, negative 12, da, 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 6, 12, do you agree with me? By the way, how do we call this set? We call it also 6z, because it says pick any integer and multiply by 6. So this is that equivalence class, but here's a very important thing. Why am I calling this, so they are all equally good, don't you agree? So I'm calling this class of 0, like someone calls California, state of Governor Brown. So can I call it someone else? My state? Can I use my name in the name of California? The answer is yes. They are all equally good. But we call them all representative. So this is my state, and I call it state of which one? Of 0, can I call it state of 6? Yes, so you can call it state of any member of that class of equivalence, although we prefer some of them for some reason. Why 0? Because that's a rename, they're smallest one and all that. But I can equally say that this is class of 1. And I call it class of 12. And sometimes we for some reason, I prefer to call it class 12. If I want, I have a right to call it using any representative I want. Is that clear? You have a question or comment?
I was asking you to choose the name to the class.
What's it?
I was asking you to choose the name to the class.
Exactly, yes. Good. And then either in another class. Class of 1, as I said, or however you want to code it, is 1, 7, 13. There's also class of 2, class of 3, I'm going to describe it, which is what? I can call this quickly 6z plus 1. What does it say? Pick a z, any element integer, multiply by 6 when you are done, add 1. How would you call this one? 4, class of 5, and then what? So this is the main thing for today, and that's what you need to practice in your homework. When you see that relation, do you know how to check what I asked in the quiz, that it reflects a symmetric transit, that's equivalence relation, and then to describe the classes. On the other hand, I also sometimes will give you partition, and I want you to understand it. But here is something that's very, very interesting, and that's, I think, a good idea to kind of announce this for what you'll do on Monday. And that's very good, very deep idea. What is the idea? How big is Z? Z is infinite, integer, agree? How many classes do I have? 6. And here is something very strange. So here are classes, they are bulky, millions of elements. They are bulky, but how many objects do I have here? Only six. No, only six. They are bulky, each of them, but I have six of them. Don't you agree? Now, can I do a little algebra between them?
Yeah.
And I'm doing the following. Say the following. How much is class 2 plus class 3? I call it in my other class, it's like playing tennis with a tennis can. So there are millions of numbers here and millions of numbers here. When I add them up, what do? I say the following. And this is important property of, that's why I call it congruency sometimes. Who should I add here? 2 and 3 or the other representatives?
The other.
Doesn't matter. Take whoever you want. You will end up, you know in which state? State 5. Why? Because here it is. Is 2 plus 3 equals 5? Yes or no? If you take something else, what happens? You will take something 2 plus 6k. Do you agree? Take k whatever you want. The other one will be 3 plus 6l. Do you agree? Then what happens? 2 and 3 is 5. 6 times k plus l. Which class is this? No matter what you choose, all of them will get you in class 5. So I can just take any representative I want. Arithmetic is always going the same way. So what happens? I have my little tiny algebra of 6 elements that actually inherits the properties of integer on a short scale. Agree? And that's called calculation, remainder calculation. So, and I can make your table. Here's the table. Addition modulo 6 we call it. Here it is. 0, 1, 2, 3, 4, 5. It is 0, 1, 2, 3, 4, 5. It is 0, but when you add 0, nothing changes. I'm not going to fit in the whole thing, but let's say you interview in any of them. How much is class of 2 plus class of 1? Do you think that in this new little algebra, does it satisfy commutative law? Yes or no? Does it satisfy associative law? Yes. And so it has many nice properties that we are used to see. Can I do multiplication here? How much do you think? So the same way I can do multiplications. So how much do you think? 3 times 4 modulo 6. Just multiply. How much is 3 times 4? Which class is this? We can call it class of 12, I don't mind, but it's better known as class of 0, do you read? So it's 0 elements. So what happens? First time you see a structure where 2 non-zero numbers, when you multiply them, you get 0. That never happened in real numbers. You start seeing some strange algebras, and people like and use them for all kinds of purposes. But we got an interesting algebra where actually 2 non-zero numbers gave you 0 number. But doesn't matter, let's do 3. How much is 3 times 3? How much is 3 times 3? 9, which is what? 3. Equation x squared equals x that normally has solution 0 and 1. Here has solution 0, 1, and who else? 3. Suddenly you have some very strange algebra, a little different from anything you saw before. And for a good purpose, this has very nice application. So for example, so what else? But something that's or also what happens with how much is 5 times 5? 5 times 5 is what? 25. And 25 modulo 6 is what? 1. Everybody, when you square it, you no. This is 1. So what can we say here? Can we say that 5 has ln. So it's whole algebra that we normally know fits nicely into only 5 elements or 6. So that's very interesting how this equivalence classes give us some interesting objects that are different from what we are used to see. Right?
So you're saying that 5 has a square root, but then 3 wouldn't have a square root, because I would say that 3 is the square
Exactly,
root. Okay.
exactly. So some numbers do have square roots, some of them. But before you would never, of course, how much is 2 squared? You know that that's 4, do you agree? So 4 did have square root before, so it will have it now as well. Whoever had it before, it will have it now, but we have some more numbers with square root. Not only 2 plus or minus square root. So we get a very interesting algebra, and the whole idea is here, saying whenever you have equivalence relation, what are you doing? You are looking at equivalence classes, and sometimes you act on equivalence classes in which way? You just pick one representative, pick the other, and you hope that they will do it in a uniform way, and then you transfer the properties from representatives into class. Do you have a question or comment?
Comment. One, it seemed that 1 would also be the square root of 1.
You're absolutely right. Yeah. So generally, although here things you should not be surprised. You know why? Because look at 5. This 5 basically, it will make more sense if I write 5 as negative 1. Don't you agree? Are 5 and negative 1 in the same group?
Yes.
So now when I write it as negative 1, you're not surprised. Negative 1 times negative 1 is what? 1. So that's why it was. So generally sometimes, so that's what I told you. I always like positives and not negatives, but wasn't it better to think of 5 as negative 1 in this setting? So that's where, when you have equivalence class, you pull out the representative that's the best for the situation that you are facing. And that changes from one example to another.
I still don't buy this, because 3 times 3 was 9, right?
3 times 3 is 9. which
And that
is
and 9 had a square root prior.
What's
But
that?
9 had a square root prior, but it doesn't have a square root now.
Exactly. But now that 9 and 3 become the same, so now it looks that 3 satisfies the equation x squared equals
So it
x.
removes some of the.
Yeah, so some properties that before were impossible, because what's happening, that's the big thing in mathematics, it's like a projection. So 2 things that were not equal in the space, when you project them, they start looking the same. And that's what happened. All right. What else I want to tell you? This is the proof, as I said. If it bothers you too much to go, it's good to practice proving, to go through this proof. But if it bothers you, just look at the example that I gave you and give you the same insight and belief in what's happening. And let me see. All right, here is one are always true. So who are they? Tautologies. Tautologies are in one state. So state of always true. So who's here? P or not P? Who is there? P implies P. Who else is here? P implies.
Not P implies anything.
What was it?
Not P implies something.
Not P.
Implies P.
And you can put anything there. This will be true.
Not P implies P. No, that's not. But for example, P and Q implies P. Oh, De Morgan's law is there. Negation of P and Q is equivalent to not P or not Q. So all those formula, are they always true, yes or no? Are they equivalent among themselves? Are they all in the same state, yes or no? That's why very often when you make proofs, you can always trade one of them for the equivalent. You choose a more convenient representative. What about P implies Q? Is that tautology?
No.
No, that's another state. Who's there? Whoever's equivalent, not P or Q, or negation of P and not Q, and so on and so on. Agree? And then there is third one, for example, P alone, and so on. So generally what happens here, then you get equivalence classes according to their root value. And that's why very often things from the same equivalence class are replaceable by one another. By the way, this has a special name, it's called Lindenbaum algebra. Yes?
Is there also one more, that's P and not P?
Thank you. There are millions of them. So for every truth table, actually, you have millions of formulas satisfying it. But in a way, on the bottom of that is exactly those are that never true, like P and not P. Contradictions are on the bottom. They actually have better organization. They have organization of a Boolean algebra. So there is a structure where on the bottom is like absolutely false, on top are absolutely true, and those in between are kind of. But it doesn't matter. Classes of equivalent formulas are formed here the same way as we have with every other equivalent relation. All right.
You
Yes.
can do algebra in between them, and it's called what?
It's called Lindenbaum algebra.
Lindenbaum.
What can you do? If you have a class of one formula and a class of the other formula, and if you want to do conjunction, what do you do? Do the conjunction between formulas and take a class with a plus.
Yeah.
And then you have operation and that operation. It's called Lindenbaum. By the name of a German proposition. All right. What's our plan for Monday? Oh, for Monday, actually what we'll do on Monday is progress more with this, when the modules are bigger, and we'll use that for encryption. So that's a neat class where we're going to show you some ideas how using those calculation modules, certain numbers, we can encrypt words and decrypt them back. So that's interesting for